I want to talk about factor graphs next. So when modeling a problem, it is best to express it as a directed or undirected graphical model, but it can then be translated or compiled into a factor graph. And that makes them interesting so that they can be used to do computations on both directed and undirected graphical models. So the result of a compilation, well, I'm not sure. So let's say factor graphs can express the standard computations in both directed and undirected graphical models. So for the example which we have already seen, I could now represent explicitly both the variables and the factors as follows. So B is specified by a prior probability, so this factor here would be P of B. Then we would have a unary factor that specifies the prior probability of C. Then we would have a ternary factor giving the conditional probability of X given B and C. And finally a binary factor saying how the probability of K depends on B. So as before, we have our variables here indicated by circles. And now in addition, we have these factors which are usually shown by these small black boxes. Now I could alternatively write this as a bipartite graph. Then I would have the variables K, B, X, and C on the one hand, on the one side of the partition, and then there would, for example, be this factor connecting K and B. There would be a factor connecting X with B and C, and then we would have these unary factors for C and B. So they explicitly represent variables and factors. We include an edge in a factor graph between a variable and a factor if and only if the variable is in the scope of said factor. Now we were talking about messages before, and they exist on these graphs also. Generally speaking, for all polytrees, the computations of some product variable elimination can be regrouped in terms of messages on this new type of graph. So in terms of messages between variables and factors. So last hour we were looking at, if you remember, we were looking at those computations here. So variable elimination in this example. I'm going to, well, show this, the same computations once more. Let's say that we are interested in the marginal probability P of x. I can then compute a something like a distance transform here on this graph. So those are all the entities at a distance of 1. Then these are the entities at a distance of 2. The factors have a distance of 3. This variable has a distance of 4 from the root node. So here we have distance 0. And because we are traversing a bipartite graph, at odd distances I always have factors, at even distances I have variables, at odd distances I have factors, and so on and so on. So I can stratify even much bigger graphical models always with respect to their distance from a particular node that I'm interested in. So I want to send messages from outwards to this node. So I would start sending a message here from level number 4, and then I would send messages from level number 3 to level number 2, from level number 2 to level number 1, and from 1 to 0. So and I'm copying the same equations that we had before. So we were interested in the probability of x. And that was given by summation over b times p of b, and the summation over k of pk given b, and the summation over c of p of x given b and c multiplied with the probability of c. Okay, so that was the equation that we saw last hour in the process of a variable elimination. And I now want to decompose it according to these different levels. So at level number 4, we're sending messages from here a single variable to a factor. And the only variable which we have at this great distance is k, and I have to resort to a special rule here, namely variables which are the leaves of a directed acyclic graph with no other factors attached other than the ones that connect to their parents. They are sending out a 1. So I'm sending out or I'm getting this 1 here. Now next, at level number 3, I'm sending messages from factors to variables. And these are the following. So on the one end here, there's P of k given B, and I'm summing out k. So this part here would be my message from a factor involving k and b to variable b. If I want to use similar notation up here for the 1, I could say that my 1 was a message mu from variable k to the factor that involves k and b. This is just the 1. Okay, but then I have other factors here, namely p of b, which is also a message from a factor to a variable. This would be the message from a factor involving only b to variable b. And then similarly for p of c, this would be a message from a factor involving only variable c to the variable c. Okay, then we're moving on to level 2. This is again a variable to factor. So let's start with this one here. This is a message from variable b to a factor involving b, c, and x. And that is a message from variable c to the same factor. Finally, at level 1, that's the entire thing. The message from factor involving b, c, and x to the variable x. Perhaps I should color code all of this a little. So let's say this was the first message here. I can plot an arrow corresponding to this message. Then we had these messages. And the rest, well, there's not so many choices left. have these two messages here going to that factor. And finally, our last message being sent to the variable x. So this is very, very similar to variable elimination. The difference is that in variable elimination, the variables are integrated out one by one. And here in a factor graph, we integrate out all variables except the ones that belong to a factor at once. In addition, variable elimination is an exact algorithm which can be used on arbitrary graphs, but we will get junction trees of very large tree width, whereas this type of message passing can also be used on loopy graphs, but it then no longer gives the exact result, but only approximate results, however, at a fraction of the cost. Okay, so now this was for one specific example. I want to write down the algorithm in general. So in message passing, we send out the following messages as soon as all the required input is available. We say that if my variable x is a leaf node, like in this example, that was the variable k, then the message we send out from this variable to its factor is 1. And if, on the other hand, we have a factor that's typically at the very top of the graph, so if phi is a leaf node in the factor graph, then we simply send out the value of that factor in itself. So those are the corner cases. And now for all the rest, we do the following. We send a message from variable x to factor phi, which is a product of all the incoming messages. So we take every h in the neighborhood of our variable. So these are all other factors except the one that we're sending a message to. And then we send messages from factors to variables. Message from factor phi to variable x. And here we see again the structure of the sum product algorithm. So here we have a summation or multiple summations. Which run over all the variables that are in the scope of the factor, except for the variable x to which we're sending a message. Now we multiply the value of this factor with the product of all the incoming messages, namely messages from all other adjacent variables except the one that we're sending the message to. I should use a capital Y here. Okay. So I've distinguished here between capital Y, where I refer to random variables, and a small y, which is the value of one particular realization. So this it's like before, we have a summation here and a product there. So what's happening qualitatively? We alternatingly send messages from variables to factors and from factors to variables, starting with those where we have all required input. So I could not start by sending a message, let's say, from this variable to this factor, because I'm still missing the input. So once I have selected my target node, I have to start at the outskirts with those variables and factors that have all the input they require to send out their message. And we're then sending messages. So here the variable phi tells the variable x how it feels about capital X taking on this value small x, given all the information that this factor phi has. And this information phi is, or the information that this factor has, is given by a summation where all unnecessary variables have been integrated out of a product of the incoming messages. So here my neighbors told the variable, or told the factor phi how happy they are with their realization small y. And so how happy the neighbors were with their value small y determines what the factor phi thinks about its neighbor x taking this small value. Okay, so this is a kind of negotiation going on in the network. And if your network is a polytree, then this negotiation is going to result in the global optimum. Yes? So this thing here, yeah. So these are, what I mean here, this is a summation over multiple variables, namely all variables in the scope of this factor. So I'm summing over all arguments of the factor except for the variable to which I'm sending my message. Sorry, this should be set of, well. Yeah, this must be a set of variables on which the factor depends. You're right.
Okay, so that's the quantity in the sum.
Yes. The scope is just the set of all arguments of a factor. So here, you see this factor represents the probability of x given b and c. So I can represent it in terms of its conditional probability table, which will have entries that depend on x and b and c. So the scope of this particular factor is x, b, and c. And here, for example, I have integrated out b, well, and integrating out c was no longer necessary, yeah? But I transmitted a message which only depended on the value of x in the end. And thanks for clarifying here. That was a good question. This is how the neighbor capital Y likes having a realization small y.
Right, but where is the small, what?
Oh,
What do we
we which says how much it likes, or how, to what extent y likes each of these realizations. So if I have y, a variable with, which can take two states, then this here would be a vector containing two numbers. And this is why, when you set up a graphical model, you like to avoid very big label spaces, because these messages then become cumbersome, become hard to compute. So you typically have different representations for a problem. For example, in image segmentation, I could give different representations. I could say I'm giving labels to the regions, and then I need at least as many labels as I like to have regions in my image. But it raises the additional problem that every permutation of these labels would give you the same segmentation. So I could have written not 1, 2, 3, 4, but 2, 1, 3, 4, it would be the same segmentation. Or you can equivalently represent this image just in terms of its boundaries. So you can have, the dual representation would be at each, when I give region labels, then I need to decide for each pixel, does it belong to class 1, 2, 3, or 4? Or I can equivalently make a representation. Now I have drawn such smooth boundaries, which I should have avoided. I can state for each boundary between two pixels if it should be on or off. And here I've just indicated the on boundaries, but then there are many boundaries that were switched off, like the ones up here or the ones here. So in this case, I then only need binary labels in order to represent a full segmentation. For this particular problem, the price you pay is that you then need to introduce additional consistency constraints, but you get away with fewer labels.
So which small y's do we plug in? Because that small y doesn't appear anywhere in the
So
So the product is over capital Y.
let's go back to this equation here. You see the first message here would say, how do we like the variable b having value 0 or 1? You see, this is a p of k given b is a small probability table. Well, and if I integrate out k, I get just 1, so that's not a good example, not very interesting. But let's take the next one. Let's say this one here. I have a number of, so this is now from the factor, which one is it? This is the message from C down there. So C could take 2 different values. So there can be cheese or there cannot be cheese. And we had a prior probability for each of these. Then we had this bigger conditional probability table of x given b and c. And I now really evaluate this thing. So by integrating out the dimension c, I obtain something which still is a function of x. Well, and b. So these are the possible different states. So you see, if you, this is something that there's a conditional probability table, and if you integrate out one of the dimensions, you still have some entries left. And these are passed as a message in terms of a vector. Okay. So I want to show an example where it's not possible to wait for all messages, or where you wait infinitely for all messages before you can send out your own. So this belief propagation only gives exact results on trees or on polytrees. I want to show a minimal example where it does not work. So let's say we have a variable a, b, and c. This is still a directed acyclic graph. We have a loop here, but it's not a cyclic loop. So this is okay, whereas a graph where we would have A, B, and C, that would not be a DAG, because here we have a cyclic loop. So I can draw the equivalent factor graph here. I have a prior probability of A. Then a factor depending on A and C. here a ternary factor connecting A, B, and C. And let's say I'm interested in the marginal probability of B. So I would send messages here. I would send messages there. And then at this point I'm stuck. Because, for example, from this factor, I would like to send a message. I would like to send a message to C, but I can't as long as I have to wait for my input from A. And here, this is why I cannot continue at this point. Now you can still use belief propagation on such graphs by just initializing the missing messages randomly. Yeah, so you can say that you initialize with random messages. And then iterate. And that amounts to a mean field approximation of your original problem. So for the physicists, it amounts to Bethe free energy. And there is a nice paper about this by Yedidia and Weiss from, I think, 2001. Okay, and taken together, this gives you only approximate inference. In reality, you would, there are many variants, such as damped. So this workaround is called Loopy belief propagation, and then one of the variants is a damped Loopy belief propagation, where the message that you send out, is a combination of perhaps 0.9, the last message that you sent, plus 0.1, the message that you would currently compute. And it works reasonably well on many problems. So bottom line is this factor graph representation is very versatile, and there are libraries implementing that. I would like to mention OpenGM2, developed by Björn Andres and Jörg Kappes and Thorsten Bayer, which is currently the most versatile library around, which is on the one hand very general and on the other hand still very efficient, because it allows you to work on discrete graphical models of arbitrary structures, so you're not restricted to grids of pixels or so. Okay, it's time for a break. And for the last bit today, after the break, I want to talk about state space models as an important particular case of